All right, let's go. Human dolphins. Yeah, it's quite interesting. So I don't know. Uh, Did we say how much these things cost? Don't it cost $30,000 or something like that? I can't remember. I'm not sure where this is. Looks like it's California to me. Of course, it's crazy ass, so it should be California. So these are the Jetlevs, I guess, doing their things. Last times, Monday and Wednesday, we were talking about pipe losses. And so we did some analysis on these, assuming that there were no losses in them. We talked about figuring out what the velocities would have to be to lift a 100 kilogram person on them. And did it once with Bernoulli, I believe, and once with, not I believe, and once with conservation of momentum. And we came up with some estimates of the power, which were a nice story, but I think they weren't true completely true because of two reasons. One, because of our discussion during conservation of momentum that if you have something held static but have with a force but is not moving, then the power there is zero because the product of velocity times force. And likewise, if it's moving at the velocity of the fluid that's squirting out, just like our vein, but there's no force on it, then you'd expect that also the power would be zero. So what we did then was a nice story and probably close to the truth, certainly within an order of magnitude of the power output, but not absolutely correct. And so what we didn't consider also is if we were trying to work out what horsepower or head pump head motor we'd have to have on it, is that we didn't account for things like losses in the system, because at that stage we hadn't talked about the energy equation. And of course the energy equation is, as we know from this week, is just Bernoulli equation with a head pump term and a head loss term on it, which is what we're doing this week for pipes. And so these are relatively significant lengths of pipes, the major losses that we talked about, from length over diameter ratios and the friction factor. And they also have minor losses in them. So your favorite subject will be addressed today. You're lucky guy. So that's what we'll talk about today. So very artistic, I guess, quite interesting machines, I guess. And that's kind of interesting what you can do with Sea-Doo as well, I guess, or jet ski, if you don't want to have the brand name included, I suppose. So that's what we'll talk about today. So that's the eye candy to get us going. So let's see what we'll talk about. 10.3. So maybe, as is traditional, we'll recap the major things that we talked about last time, so that if you didn't turn up last time, you don't miss anything. All recorded. We'll talk about the energy equation, we'll talk about Moody chart quickly, and then we'll talk about these minor losses, which are losses in fittings, and also entry and exit losses are also minor losses that are associated with it. And maybe if we have time, we'll go back to the Jetlev just for kicks. So we wrote some things down last time. So it's probably easier just to go through those than rewrite them. We talked about the fact that the energy equation is just the same as Bernoulli, but what it has attached to it is some extra terms. It has a pump head, which we have to add if we have losses in it. And it has major and minor losses attached to the end, which are these two terms. They're the sum of all the major and minor losses. So you have multiple pipes in series, then you have multiple components to sum. My dog whistles, heard a high frequency sound then. We know that we have to write it from upstream to downstream. That's very important. So the left-hand side is upstream. Pump heads are given by this, which is the power that's applied, the mass flow rate, which is these two terms together, and gravity. Positive if it's a pump, negative if it's a turbine, always on the left-hand side. Major and minor losses come from either pipes or for fittings, or entry and exit losses, as we'll see today. They're always positive because energy is always expended. If I drag something across the table to get it to where it is, I've expended energy to do it. If I push it back to its initial spot, I've also expended energy against friction. Friction always acts against flow, and this is basically friction that's acting along the pipes, and which gets dissipated in heat. You're doing thermal after this, so you can relate to that. And we talked last time about what these major head losses are. They're how long the pipe is relative to its diameter, what the velocity is in the pipe. So this is the pipe velocity, average velocity in the pipe. We talked about the velocity profile within the pipe might be parabolic, where it's stuck to zero velocity at the edges of the pipe. It is, in fact, if it's laminar. But we assume that the area under this velocity profile is replaced by an equivalent prismatic area, so it's just the average velocity which we use. And it has to be the velocity in the pipe. It's not the velocity in the tank, which of course is zero if it's a big tank, or going into the pipe. It's actually the velocity in the pipe. And likewise for the minor losses. And we can characterize this frictional term is really just an Euler number, which is equal to the pressure, change in pressure, density, velocity squared. And so this is the same term that you get if you're squirting a jet on someone and it stops, the velocity goes to zero. This is the magnitude of the pressure you developed as you kill this velocity. So it represents a force that's applied on the structure. When we're looking at pipe flow, that force is applied on the water that's going through the pipe and slows it down. So usually in this, we're interested to find out what the velocity is and what power we have to apply to work against friction. If we're working on a turbine, wind turbine, the velocity of the air around the turbine doesn't change very much, but it's the forces that are applied on the turbine that we're interested in, because that drives the motion. And so they're almost exactly the same problem, which I tried to point out in kind of a tortuous Monday. I thought probably went down a rabbit hole. But with this exposition here, it's not here. I thought I talked about, oh, I guess it's later. Well, yeah, I guess it's another file. I won't go there. But for external flows and internal flows, they work the same. And so all we need to figure out is the magnitude of this friction factor, or Euler number. We can use experimental evidence for that, and we use the so-called Moody chart. If you need it on a test, Parker's question, you'll always be given it at the end of last class. And so we know that there are two regimes. We know that there's a laminar regime. We know that there's a turbulent regime. And it's usually divided by something like 2,000 or 2,200. Reynolds number is the ratio of inertial forces, velocity, a density, times a characteristic length, divided by viscous forces, viscosity. By definition, this is usually the diameter of a pipe, or it could be another relevant characteristic dimension. And it really indexes how big the velocity is. And I guess it's not so apparent in a pipe, but if you're looking at flow around a cylinder, then turbulent flow around a cylinder would be this, with vortices, versus this. Oh, waited too long. And the same on the bottom. And so this is creeping flow. The resistance to this flow is due to, I know we're talking about a pipe, but the same idea. The resistance to this flow is the viscous friction on the edge. On here, actually you can think of it much more interestingly as this is a pressure on the front and a different pressure on the back. And this drop in pressure between P1 and P2 is the cause of the forces that are the drag. And so viscous drag versus pressure drag, it's the same inside a pipe. It's really viscous drag on the side of the pipe that I kind of drew up here with these little arrows versus a drop because it's all winding all over it. And so that's interesting because then the turbulent regime, the friction factor is a function of, could be Reynolds number and relative roughness. So this is relative roughness. Relative roughness is just the roughness on the edge of the pipe. This is epsilon. This is diameter. I know I'm repeating myself. Important stuff, though, of course. Kind of boring, but I think important. Well, perhaps it's all boring. And in the turbulent regime, the friction factor is also a function of Reynolds number and relative roughness, maybe. But we know from these results that certainly relative roughness doesn't apply here. Certainly it's a function of Reynolds number because we know that this curve here, the equation of this curve is that the friction factor is equal to a factor which happens to be 64 for a circular pipe over Reynolds number. So it's inversely proportional to Reynolds number. And so as Reynolds number increases as you go along in this direction, of course, the friction factor decreases in this direction. So that's just this equation. So for laminar flow. It turns out that there's this transition region, and for a smooth pipe, it's kind of a bit like laminar flow. It's also not a function of relative roughness, but this locus of curves here is for a smooth circular pipe. And so that's also a function of Reynolds number, but not relative roughness. But in the turbulent regime, it's the opposite. It's not a function of Reynolds number because you see that these curves are all horizontal. So if you double Reynolds number, triple, quadruple, or multiply it by a factor of 36 times, the Google fine, 10 to the 36 rubles, know about that? Yeah, more than the money in the world. So if you multiply it by a factor of 10 to the 36, also the friction factor doesn't change, turbulent flow. And so that means that we deal with these differently, which we'll talk about in due course, probably on Monday. It turns out that if we solve for the head drop as a function of this, because this friction factor in the laminar regime is a function of velocity, it's a function of Reynolds number, then this v squared term goes away and we get a velocity directly out of this, straightforwardly. If friction factor is not a function of Reynolds number, then we're left with the v squared term. And when we do the calculations for the velocity, if we have a pressure drop, then we have to square root the velocity term. So we'll talk about that in due course. Didn't talk about this figure. This figure is just if you have a diameter of a pipe and you have different relative roughnesses on that pipe, you can calculate the relative roughness as a function of that pipe. It's just the same as knowing what the roughness is and dividing one by the diameter. If you know what the pipe type is, I'm not sure. So I guess this would be drawn tubing, which is smooth, riveted steel, which is not smooth, and so this would have, for a given diameter, a larger relative roughness. Larger in increasing values. And typical values here, and of course the Moody chart, which we just talked about. So that's kind of where we are. So I won't talk about that again. So I don't know whether it's worthwhile writing out the Bernoulli equation again. Maybe. It's easy to do. So remember, I hate to repeat myself, but I do, I know. Upstream and downstream, head losses, head pump losses, or pump inputs, and downstream. This should be emblazoned on your psyche, so you should know this term by now. And the two summation terms. Sum of head losses major. Incrementally they're small, but over the long lengths of pipe, they're large and minor. And I guess they are always given by this equation, which is the head loss is equal to a friction factor, how long your pipe is versus its diameter, and the velocity in the pipe squared over 2g. I won't do an overbar so it doesn't look like a -2. And the head loss due to majors would be individually KL multiplied by V squared over 2g. And you just, if you've got a bunch of fittings in the pipe, you just add them all up. I suppose since we now know that this friction factor is a function of Reynolds number in laminar and independent of Reynolds number turbulent, this is usually just a number that's given. So I guess the assumption is that these loss terms, K loss factors, are always assuming it's turbulent because it's usually just a number. And so we can look at what those are if we just look at, go back to the book. I'll come back to that. I want to go to the jet levs again. Don't care about this. We've just done this. Take it as a fact that it's that. It's basically the idea that if you're going from zero velocity to a non-zero velocity, then you're accelerating the fluid, and so you're applying some energy to it to move it against inertia, F equals ma. And so in going from zero velocity to some velocity, there's some energy that's expended in the system, but you never get back. And I suppose the message is that this loss coefficient, KL in this case, are these magnitudes here. And you see that as it's most disruptive, that you're accelerating stuff around corners, then you'd expect maybe this magnitude to be larger. And if you ameliorate that by having a nice smooth entry into the system, that you're slowly in space accelerating from a zero velocity here to a small velocity, to a bigger velocity, to the maximum as you get in the throat of the pipe. You can tell that just from continuity, that the loss coefficient is less. It always seems to be less than 1, and we'll talk about that a little later, why that should be. And it occurs in different ways. We shouldn't probably spend too much time because it's a not very relevant part for this course. If you have fluids that are accelerating, then potentially you get a so-called vena contracta, and that is that there's a dead zone around the edge of the pipe where the fluid isn't moving, but this is fluid filled, and it comes around the corner, it's screaming around the corner, its car, it's got some momentum in this direction, can't quite turn fast enough, and so it misses this zone here. And actually, you know, I remember that I was asked the question of why do you get vortices around things. One better explanation from roughness, although roughness is one, would be that as you have stuff, no, I don't want that. As you have stuff screaming around this corner and then put in this direction to go this, from F equals ma, and I guess not so much that every object in motion will continue its same path if you don't act on it with a force, this will want to go here. If it wants to go here, there's a whole zone up here that doesn't have anything in it, so continuity requires that it gets sucked in, and it gets sucked in because there's no material in here, and the stuff going around here would just form eddies as it goes down. And so these are the von Karman vortex street, which is the reason for Tacoma Narrows, that it wants to go here, there's a void here, it fills in because if there's a void, there'll be kind of a slight vacuum that pulls it in, and so it'll move. And so the reason for Tacoma Narrow, as we said, that is if you have a bridge deck that air is flowing over, then you can treat it a little bit like a cylinder. And what it will do is it will shed an eddy on the top, and then the next little while it'll shed an eddy on the bottom, and it's like plucking a guitar string, this thing that goes into the page. So that's what a vena contracta is. You can calculate what that magnitude would be. Let's not worry about it. You can define those magnitudes. Again, the losses are, as we'll see if we do an example, small. They're less than 1. Doesn't mean that relatively they're small, but they typically are small. And as you get a smoother entry, which is the radius of curvature of this increases, then R over D increases as this gets smoother. I guess a radius of curvature of 0 would be this, right? And so that would be the worst case. Exit losses, you have the same deal. You have something traveling with a velocity, and all of a sudden, bang, it stops. Like the truck on the tarmac at San Francisco, same idea. It goes from some velocity, that was at zero pressure. This clearly has a pressure, to zero velocity, not necessarily completely stagnating, but these terms tend towards unity. And it's because you're using up all of the pressure that's driving this flow, and as the velocity goes to zero, it's expended, so you're expending this. So I suppose you could think of it almost as P1 minus P2 over gamma equals, on the right-hand side, it would be V2 squared minus V1 squared over 2G. And you could think of this as pre-multiplied by a loss coefficient, which is really why this would equal 1. No, don't need to worry about that too much. Same deal, we can deal with entry losses and exit losses. Same idea for contractions in pipes, that the losses should be some factor. So where you go through a change in diameter, you might have to put a loss coefficient here and apply it to the right velocity. In this case, it looks like it's V2, the downstream velocity. So I guess if the velocity changes in the fitting, you have to be mindful of what velocity you're scaling it with. And then a little analysis here, which takes all the things that we've held near and dear. We talked about conservation of mass. We talked about conservation of momentum. This is just our momentum equation, which is kind of Bernoulli written more generally. And we talked about the energy equation, which is Bernoulli, but with an extra term in it for loss. If you throw those together, I'm not going to do it, you end up being able to calculate the loss coefficient for this expansion as being equal to 1 minus the areas. I remember seeing this morning. This is not that you care, this is A1. The loss coefficient is equal to 1 minus A1 over A3. So A1 is the upstream, A3, I guess it's 2 in this particular case, A2. If A3 is very big, then this term goes to 0, and the loss coefficient is equal to 1 squared. And if A2 is the same as A1, 1 minus 1 is 0, and so it'll be, there's no loss, which is what you'd expect. So those are what we deal with. Going around bends, you could calculate what they would be, all kinds of deals. And typically, since these loss coefficients, as I said before, are just given a magnitude, not as a function of Reynolds number, then they really are for, the assumption is turbulent flow. And so these losses, I said before, they seem to be between 0 and 1. I guess that's not true everywhere. Not sure what makes it bigger than 1. But as you go around bends, the more severe the angles and the more severe what's going on inside, whether it's a flange or whether it's threaded with lots of resistance, you'd expect to have more loss of energy on the friction against threads. Then you can choose your loss coefficient for that. If you're going around a more gentle bend than 90 degrees, then you'd expect it correspondingly to be less disruptive. I guess we know that momentum is equal to mass times velocity. Velocity is not just speed, but it's also direction. And so this is changing direction, if not speed, as it goes around the bend. So the momentum is changing. A bigger loss if you're going around 180 degrees because you're changing your direction completely. T's mean that this is closed. So in other words, I guess let's not think about that. So if you think about this pipe being closed here, then there's a disruption. I guess you could imagine that it will want to swirl around here in going on. This would be stagnant within this region, but this is for a closed T where there's not flow going up it. If you have a T where there's flow going up it, which I guess would be a branch rather than a T, then you have more disruption because it's going around 90 degrees. This is just going straight down. Some of the flow will be enticed into this because it's not a solid wall, and it will do something strange, you could imagine, and therefore there's a small loss from that, but not as big as if it branches and goes around a corner. And if you have a union which is threaded, that means that I guess you'd have threads in here and threads in here, and this gap, I suppose, would be here. Again, you'd have things wanting to go down here, but mainly it's this flow velocity. And again, in all of these, the velocity is the average velocity in the pipe. You don't have the problem if it's not changing diameter that the velocity is changing, but it's just that velocity. Valves, I guess, also would be an issue. You control flow in valves. I guess the way that this works is that you screw this up, and now you allow flow to go into here, through this and out. And so it goes around a bend. It's forced to go around a bend. I don't know what this is. This looks like it's an anvil that gets lifted. And so what was blocked flow going through here that couldn't get going through here now is able to go through here. So they'd have just a different amounts. So these would be those, who knows, bull valves, gate valves, globe valves. I don't know what those are, but they're shown here. Check valves that go through, these are valves that might have allow one-way flow. So you can flow this way through this. If you have a pressure upstream, it'll open this hatch because there's push against it. Maybe it's got a spring that's keeping it closed. If you flow the other direction, it'll stay closed and it'll only allow one-way flow. So that's it. So we could go home now, but I guess it's 25 minutes in, or we could play around with the JetLev. I thought we'd do that. So on Monday we'll start solving some problems for flows in pipes, so-called type 1, 2, and 3 flows. We already did a type 1 on Wednesday, where we know the velocity and we can calculate the Reynolds number. And type 2s are just when we know the geometry of the pipes, but we don't know the flow velocity. And that becomes an issue because we said that the friction factor in these, it doesn't matter for these fittings, but the friction factor matters if we're doing pipe flow because it's a function of Reynolds number. And we need to know the Reynolds number. We need to know what the flow velocity is. So we just know the geometry of the pipe, and we're guessing what the flow velocity is. We have to go through an iteration to get it. So I thought today I'd play around with the JetLev to be able to illustrate our favorite topic, which is minor losses from last time. That's the next one, right? Where did I miss it? Yeah, okay. So I moved some stuff from my notes here. So you may recognize this. This is, we did this twice. So enjoy yourself. Just absorb this. This is the JetLev. And we've seen this before. You have this in your notes somewhere if you're writing down. Lev, I suppose, not the, isn't it a Jewish name? Is that Lev? It's levitation, I suppose. Remember when we're talking about Bernoulli, we're talking about pressure, velocity, and head losses in Bernoulli. And we talked about being able to, that as you go through a system, these are conserved. One might go down and it will do it at the expense of another. We realized that if we wanted to do the JetLev, we could write this as the backpack, the stream of water coming out of it, coming out at some velocity. The pressure as it comes out, because it acts uniformly in all directions, is 0, but it certainly has a velocity. Where it hits the deck, it has 0 velocity and will develop a pressure because we kill off all that velocity. And so we could write Bernoulli for that and see what we know. If we did it right above where it hits the water and where it hits the water, this has 0 pressure but a velocity. This has 0 velocity but a pressure. And if we do that, we can write Bernoulli on both sides. We end up with this expression here, as we did. Perhaps I got my equations and calculations right. And we'd end up, in this case, with a v-squared term. So here we're just killing momentum. And so this is, as I said earlier, 2 regimes. Laminar regime in a pipe, function of Reynolds number. And so we end up with the behavior being proportional to the velocity directly. Turbulent regime, we're destroying momentum between upstream and downstream, just like hitting the sphere. And so we end up with this velocity squared term. The drag is due to pressure drag, not due to viscous drag. Two very different mechanisms. And if we do that, we can calculate in terms of a velocity that is balanced with the weight of the person hanging off this. So this is the weight of a person, just a mass balance, force balance. And we ended up with 10 meters a second, roughly. We'll use that. And so we did something, we said that we could get the amount of work. So this is W dot, which we've called it, which is force times velocity. And if we know what the force is applying by the weight, which is 100 kilograms, which is 1,000 newtons roughly, and we know the velocity of the flow coming out of it, then we take the product of those and we got 14 kilowatts. Okay. Kind of a nice story, but actually from what you know now, not really true, right? We talked about forces being like this. And I'm going to work up. So we talked before about velocities of control volumes. And we talked about forces. This is the weight of the person, not the work. And so we could think of it that either you're applying a force, actually force is downwards because of the person, and the water that's coming out of here at some velocity provides two cases, right? You can either have a force here and the fluid velocity is coming out, but the velocity of the control surface, if you like, is zero. And so in this particular case, you have a weight which you're acting against, a force, but the velocity of the control surface is zero. And so you'd be at this point here. If you release this force, you know that the velocity of the control surface will go at the velocity of the jet coming out of it. It's like the vane example, pushing the vane across the floor. And so if you release this force, then the velocity that you'll travel at will be the maximum velocity, but the force acting on it will be zero. So you'll have this portion here. And so if you look at those magnitudes, then if you look at the magnitude, you can imagine that between those, if you take some of the weight off it, then it will start to move at a velocity. And so you can imagine it would move along this trajectory. And so now if we write down the work that we need, which is a different W, which is force, which is W times velocity of the control surface, then at this force here, we have zero velocity by definition. So the product of those two, we've done this before, is zero. At this velocity, we're not applying a force because we say we can only go at that velocity if we take the guy off there. And so there is no force, guy or gal, so we're here. At this point here, maybe we have a half W, and we also have a half VCS. This is the maximum velocity. And so maybe we would think about this could be our system. Maybe this peak amount here is a half times a half of the weight times the velocity of the control surface. We know that the maximum velocity of the control surface, of course, is the velocity of the water coming out here. That's kind of a hint. And so rather than the work or power that we need being this, maybe it's a quarter of this for that argument. To have work done, you have to have not only a force that's applied, but that force has to be going through a distance. Work is force times distance. Power is force times distance per unit time, or force times velocity. And so, nice story, but right order of magnitude, but perhaps not correct. completely. And yeah, and we solved it solving it another way. So coming back to what we're interested in now, I guess. So we could have Johnny or Janie sitting on this thing. And what's the best way to draw this? I don't know. And I suppose, yeah, so how would we solve the problem? So now, I suppose we have a pump in our system. We could write the behavior in terms of this as being a whole bunch of points, right? This could be 1. This could be 2. This could be 3. This could be 4. This could be 5, I suppose. This could be a velocity. And we could try and solve that. So if we write Bernoulli for that, if we put some numbers in it. So write Bernoulli. So we'd end up with C1 minus C2, just come from here, plus V1 squared minus V2 squared over 2G, plus P1 minus P2 over unit weight, plus the pump head is equal to sum of friction factor, length over diameter, V squared over 2G, plus the sum of KL, V squared over 2G. So I guess importantly, upstream, downstream, pump head, sum of lost terms in the system. So what will these be? I guess we could give it some lengths. I don't know. Let's make life easy. Let's make this 2 meters. Let's make this 6 meters. Let's make this 1 meter. Let's make this 1 meter. So it's 10. What else do we know? We had a velocity which was 14 meters a second. I don't like that. Which would hold us. What else did we need? I think we needed a cross-sectional area. I chose a diameter which is equal to 10 to the minus 1 meters, 4 inches. So the area equals pi d squared, but let's just call it d squared, which is 10 to the minus 2 meters squared. Let's move planets. Not 9.81. And then figure out what we do here. So Z1 minus Z2 is, it's negative Z2. So I guess why don't I just write these things in? So this is 0. This is 2. A conundrum, I guess, here. This is V1, which is probably 0. But we have to get it into here. You could imagine that we could have an entry or an exit loss here. Let's ignore that. Well, actually we could do it, I suppose, in here. V2 is this. No, this is V5. So maybe I should relabel those that. This is V5, isn't it? So V2 will be equal to 10 meters a second. P1, it's on the surface, 0. P5, it's come out of the system, so it's already in the air, so that's convenient. That's also 0. HP will not be 0 since it's driving it. And we have to look at these components on the other side. I'll write my equation here. So we would have the friction factor times length 1, 2 plus length 2, 3 plus length 3, 4 plus length 4, 5. I guess individually over D is the same in all cases, so I guess if we're taking D as the same, then this is the same, times V squared over 2G. This V squared is the same as this one, right? We'll just make life easy, same as the diameter of the pipe. And we'd end up adding onto that, we'd have pipe loss 1 plus pipe loss 2. I'm going to get tired of writing these. Perhaps I won't write them. It keeps on writing them, having said that. So there'd be an entry loss, there'd be a bend, there'd be a bend, there'd be a bend, there'd be an exit loss, I suppose. And I guess we could see how big these are relative to these are minor losses. And it's V squared over 2G. And again, this velocity would be velocity 5 if we want it. It's not really velocity 5. It is in our case because we've chosen it to be that. So actually, I'm not going to write that. And so we'd want to solve that. We don't know what the friction factor is. So we have to calculate Reynolds number. Reynolds number is just a velocity times a density times a characteristic dimension, which for these is the diameter of the pipe, times viscosity. And if we use round numbers, this is 10 times 10 to the 3 kilograms per meter cubed times 10 to the minus 1 divided by viscosity of water, 10 to the minus 3 Pascal seconds. This is meters per second, kilograms per cubic meter, and then meters. So it should be dimensionless. So what is that? This is 10 to the 4, it's 10 to the 3. I guess conveniently that and that cancels. Even I can do that math. Well, I was going to say it's 1, but it's not. It's 10 to the 6. Is that right? So it's 10 to the 6. I don't know where our Moody chart is. Let's assume it's smooth. And indeed, it's this. This doesn't extend down that far. So it's 0.01. This is be 0.011, 2, 3, 4, 5. So this is 0.11. Interesting enough, if this laminar regime could be extended to this, it would be also roughly almost 0.01. And of course, 0.01 friction factor for a laminar, that doesn't quite work out right. Friction factor is equal to 64, yeah, forget that. So Reynolds number is 10 to the minus 6. It should be 64 times 10 to the minus 6, right, if we're there. So it's not quite that, so I don't know. Yeah, well, let's not go down that rabbit hole. So our friction factor is 0.01, 1 over 100. And so friction factor is equal to 0.01 equals 10 to the minus 2. And I suppose we could do some math here. What do we want to know? This is what we want to know. So if we keep it on the same screen and moving everything over, HP is equal to 2 minus 2, which would be 2 meters, right? Right? Hold on, so that's not quite right. So I guess 2 meters needs to be to this point. So that's, assume we're 2 meters off the floor. It has to be H5, Z5, right? So that's 2 meters. So we're left with negative, so it's plus 10 squared over 20, 2g. This is 0, so we don't have to worry about that. This is on the left-hand side still, and we're going to add these other terms. So we have the friction factor. So this is 0.10 to the minus 2. The lengths were 6 plus 2 plus 1 plus 1, I think. 6 plus 1 plus 1 plus 2, I guess the other way around. This term came earlier, but that's fine. Over D, which is 10 to the minus 1. And the minor losses. Don't know what the minor losses should be. We're going around corners and things. What were some good numbers for that? Probably easy to take ones. I don't think that hurts us too much. If you're going around a corner of the order of 1, it seems that it's less than 1, but let's just assume 1. Always positive, bless you. And so this would be 1 plus 1 plus 1 plus 1 plus 1. Should be 5, right? And v squared over 2g. This is also, and I missed that out, right? And so if you look at what those numbers are, actually it'd be convenient, I suppose, to keep this as v squared over 2g, rather than put the numbers in. And so we have the pump head is equal to 2 meters plus 1, which is this term, plus 10 to the minus 2 times 10 over 10 to the minus 1, plus 5, and if I put the brackets in the right place, you're probably ahead of me. We end up with that. And so it's useful to look at that because we have 2 plus these individual terms are 1 plus 10 to the minus 2 times 10. That's not 10 to the minus 2, right? Why did I do 10 to the minus 2? What did I... Oh, friction factor times 10. Okay, that's right. That's the length. And v squared over 2. So that's 10 to the minus 2 times 10. That's 10 to the minus 1. 10 to the minus 1 over 10 to the minus 1 is 1. Plus, so actually in this case, the losses going around the bends end up to be large. Surprises me that that's the case. Yeah, they're both operated on by the same velocities. This is also the same velocity that's coming out of the system. So this is v squared over 2g. And so if we put the numbers into that, we'd end up with the pump head is equal to 2 plus 7, which is equal 9, which is about 10, times 10 squared over 2 times 10, which is a pump head of, this is 10 divided by 2, which is 5. So it's, I think it's 5 times 10, which is approximately 50. Units have to be meters. It's pump head. And I guess 50 is greater than the 2 meters that it's going up and coming down, which is good. And if we wanted to calculate the power, I know we're right at the witching hour. We have pump head is equal to power times density, volumetric flow rate times G, which is power is equal to HP rho QG. Q is equal to velocity times area, which is equal to 10 times 10 to the minus 2, right? 10 to the minus 1 times 10 to the minus 1. And so this becomes 50 times 10 to the 3 times 10 times 10 to the minus 2. This term here is just Q, and multiplied by 10 meters per second squared. So that is equal to 50 times 10 times 10 to the minus 2 is 10 to the minus 1 times 10 is 1 times 10 to the 3. I think you're left with that. Is that right? Check my... Yep. So that's the power. You need to run it. Order of magnitude. If we did this by our previous calculation, we ended up with 14 kilowatts. And so, yeah, this ballpark magnitude. We said that this estimation wasn't right because of this argument that we had here. Where did I put it? I don't see it now. Yeah, this argument here, that maybe it should be a quarter of what the real magnitude is. And so what the real magnitude with those losses is 50. A quarter of 50 is 12.5. Actually turns out to be pretty close to 14, which is what we had here. And that's just a way of being estimating that. It looks like a respectable number. I don't know what it is because I didn't do it before, but I thought it'd be kind of a fun thing to do. So that's how we might size a motor for doing that. So the moral of the story is we just need to use the energy equation, which is this, upstream to downstream, always positive, all positive for a pump, negative for a turbine. It works out to be positive in this case, so it's a pump, and it allows you to estimate things. Always a good thing on tests actually as well is to estimate whether your number that you're getting is right by using 10 meters a second. Probably also on tests, if you use 10 meters a second, because the answers are plus or minus 10%, you'd probably be right every time as well, I'm guessing. Sorry. Thank you. Is Nelson holding class today? Good. I thought he might be. Good. Have a great weekend.